Now I would like to invite Mr. Josef Kveton to present his paper, Influence of Inertia and Material Properties on Discrete Simulation of Dynamic Fracture of Concrete.
Good afternoon, ladies and gentlemen. Sorry for a short delay caused by non-working PDF file, which was probably my fault. Anyway, my name is Josef Květoň. I am a PhD student from Brno University of Technology in Czech Republic. And I am working on dynamic simulations of concrete fracture using a discrete particle model. Okay, so let me begin. But before I begin, allow me a few words on the reason why we use discrete approach instead of continuous models. Every time we choose a model for the problem we want to investigate, we need to take into account the phenomena that we want to investigate. And since we want to investigate the fracture of concrete that initiates and the crack grew at the scale of material where we distinguish individual aggregates, the material is quite homogeneous here, quite heterogeneous here, and so we decided to use the model that already incorporates the heterogeneities of the material by its very nature. Here is a brief outline of my presentation. I will describe the model, then I'll talk about the dynamic solver, and in the end I'll show you the results of the numerical simulations. So, discrete model. The idea behind the model we are using is following. We can use a fine lattice of brittle elements. We can project the material structure on this fine lattice and assign elements different behavior according to aggregate, cement paste, or interfacial transition zone. Well, this is fine, but in the end it leads to a system with a large number of degrees of freedom. So we directly represent only the larger aggregates in concrete. We represent them as particles. The particle structure in our model is generated by Voronoi tessellation that is applied on a set of points randomly placed in a volume domain within a prescribed minimum distance. Yeah, that's it. And in 3D, the Voronoi cell is a polyhedron. It is important to know that the model is adopted according to the work of Professor Koussatis and his team. The idea behind using this particle model instead of fine lattice model is saving computational cost. The particles are assumed to be ideally rigid, and their interaction happens only at the contacting facets. So, something about constitutive relations. Of course, in elastic behavior, we use two parameters, elastic modulus and ratio between tangential and normal stiffness. I denote them here as E0 and alpha. And since they are applied at mesoscale, which is the scale of individual particles, they are different from overall material behavior that is described by Young's modulus and Poisson's ratio Ni. Anyway, their relation can be derived from principle of virtual work, and yeah, it's stated here. In nonlinear regime, damage model is applied. yeah, important is the damage parameter D that lies between 0 and 1, including both edges. And its evolution between 0 and 1 is crucial for the model behavior. 0 means intact material, and 1 means that the material is not able to transfer any load. Two important things. The damage is irreversible, which is stated here as Dmax means maximum previously reached damage. And maybe even more important, it is dependent on the straining direction, which is described by angle omega, which gives us more information about the combination of normal and shear loading. And of course, it is also important if it's positive or negative. Okay, something about dynamics. We are solving equations of motion. M, C, and K stay for mass, damping, and stiffness matrices. F, loading vector. U is displacement vector. We are using implicit time integration scheme according to Newmark. So the time derivatives of displacements, here accelerations and velocities, are calculated numerically according to these equations. And if we substitute them into equation of motion, we obtain the system that is in the bottom of the frame. It is important to note that we omit damping, so every term that is multiplied by matrix C can be thrown away. Fine. But what about the mass matrix? Every particle has 3 translational and 3 rotational degrees of freedom. So it contributes to the global mass matrix by 6 times 6 matrix that consists of masses, inertia tensor, and then there is a part that I call static momentum. Why is it there? It's simply because the center of Voronoi cell does not necessarily need to be the center of gravity of the polyhedron. Okay, so this brings me to the results of the simulations. We simulated L-shaped concrete specimens that were 500 millimeters height and width. Thickness was 50 millimeters. The specimens were fixed in the bottom and loaded vertically from bottom to towards vertical direction. The experimental study was performed by Professor Oshbold and his team. And the material parameters for the model were obtained from fitting the quasi-static response. Yeah, and here you can see the relation between peak load and the displacement rate. The reds are results of the model. Black squares are experimental data. You can see that for displacement rates larger than or faster than 1 meter per second, the error is getting bigger. I'll come to this a bit later. Now I'll talk about something, not else, but something related, because it is not only the maximum load that is important, it is also the correct pattern that is important. Here, the correct pattern is displayed as, you can see here, the elements or the particle contacts of the model, and they are colored according to the value of damage that they obtain. So more red means more damage, then the red is the correct. First, have a look at the middle row, which is refront simulation. I'll come to the others a bit later. You can see that the correct for the quasi-static loading approaches vertically, horizontally, and with increasing loading rate, the correct inclination angle grows up to vertical, and with further increase, there is correct branching, which corresponds to experimental evidence up to one exception, and that is that no crushing of the material in the area of applied load was observed at experiments. But we wanted to know what part of this strain rate dependent behavior can we address to, let's say, structural behavior or inertia effect and the increased material resistance. So what happens if we change the strength of the material? If we apply weaker material, we can see that the correct inclination angle is bigger and the correct branching happens for even smaller displacement rates than for the stronger material. For quasi-static loading rate, you can see that there is no change in the correct pattern, and there are large changes for the load displacement response. If you have a look at this velocity, 0.35 meters per second, you can see that there is almost no change in the load displacement curves, which means that the loading force is here dictated by the inertia and then the mass density. Okay, so what is the problem? The problem is that for the higher velocities, the phenomena that, or the cracking happens under the resolution of the model. So we need to capture it somehow in the constitutive law. So we adopted strain rate dependent constitutive law, where is a strain rate dependency function which takes into account the rate of crack opening of any individual contact of particles. And we can see that for specific values of parameters that we apply to this function, we are able to avoid the cracking in the area of applied load. But there was another problem. We were not able to obtain the loading force comparable to the experimental evidence, especially for the higher loading rates. But the problem was that the force sensor was as close as possible to the experiment, but still there was some small steel mass between the sensor and the specimen itself that affected the response. So if we modeled this directly, we could obtain the much higher loading force that is comparable to the experimental evidence. You can also comment on the smoothness of the numerical response, which is mainly caused by the fact that in the numerical simulations we can keep the loading rate constant for the whole loading, which is nearly impossible for the experiment. Okay, so far I've been showing you the results of the simulations using deterministic material properties. Now we apply the random field on the material properties, on the material strength, and also on the fracture energy. Here you can see that the blue color denotes the weaker material and the red color denotes the stronger material. And here are the correct patterns for each material properties distribution for 3 different loading rates. You can see that there is only slightly changing the load displacement curves, but the change in correct pattern is quite large here. Okay, this brings me to the conclusions. First, which is already well known, that the strain rate dependent material behavior can be addressed to 2 phenomena. One is inertia effect and the other is increased material resistance. Then for this model is able to represent this kind of strain rate dependent behavior, but only up to the resolution of the material structure that is directly modeled. Any other things that are not captured by the resolution of the model need to be captured by constitutive law. And in the end, I can have a small comment that the material strength is mainly responsible for the changes in crack pattern, and the mass inertia is responsible for the changes in loading force. Okay, that's it from me. Thank you for your attention.
Thank you, Mr. Joseph.